Written language is one of humanity's most important and transformative technologies. We may not think about writing or alphabets as technology, but beginning with cave paintings and working forward into hieroglyphics, cuneiform, Gutenberg's movable type printing press, Xerox copies, and now even with modern digital images like the portable document file, throughout history, people have written important things down. We tend to record important things that happen and important and complicated collections of facts in written form. Today, we live in a data-driven world. And as developers and technologists, we're trying to develop ways to support decision-making that can be very data-driven. The challenge that we have is that documents are unstructured. And so from an engineering or developer perspective, documents are unstructured data. What we're trying to do to leverage document data in decision-making is to structure the data. And to do this, we need to talk about how we can process raw unstructured data to create highly structured usable data, or rather, how can we use very powerful tools that can enhance and improve our ability to have humans working directly with unstructured data. Today, we're going to take a look at two of my favorite things: AI agents and document intelligence. Before we jump into the AI conversation, let's make sure that we frame the document problem as a data challenge. So we all know, what a document is, right? So here we may have a document, we'll call it document one. And, inside this document, documents tend to have like a title and may have a lot of words. Some of our words are short, some of our words are long. If we're lucky, maybe this thing's got some structure like some paragraphs. It's going to have some punctuation throughout, etc. Now, we know in a variety of environments, business environments, that we're going to also come into documents that have a lot of words, like document one, but then, they're going to have tabular data oftentimes. So we may have examples of tabular data, like a 2x4 table, and then we may have a more complicated table down here that looks like a what? We did a 5x3 down here, okay? Now, we know that documents are going to contain, words and punctuation. We know they're going to contain tabular data. But another thing that we're going to see is, some documents are short, and some documents can really get very long, can get long and quite complicated, right? So we can get documents that are 600 pages plus. Word counts really start to take off on us. And then over here, document four may be an example of something like document two, where we've got words, in tables everywhere. And we can start getting into complexities like tables that run across pages, right? So we can get into lots and lots of pages, with long tables. Maybe we have tables, with in excess of even 10,000 rows. So this is our document space. And so this can be viewed as traditionally as an unstructured data problem. Okay. And when we run into practitioners who have wrestled with this problem in the past, the technology we always hear about is optical character recognition. And what optical character recognition does is it's able to use computer vision to go through this document and to recognize different characters and words, and it's able to translate these into text. With OCR, you can even have some luck perhaps recognizing tables, but we get into real trouble, when we run into things like page breaks. And when we translate data with an OCR, we don't have any real semantic understanding of what we've done. We've really just accomplished creating a lot of text. Okay, so let's keep that problem in mind. The other thing that we want to talk about with documents is that any one document is not that valuable because documents tend to relate to one another. Okay, so let's talk for a quick minute about what we call hierarchies. Okay, and with hierarchies, we have vertical hierarchies and horizontal hierarchies, okay? And what we mean by hierarchies are how documents in a population relate to one another to create a logical whole. Here are a few examples. Let's imagine that we're in sort of a financial legal use case and we have a master service agreement as a contract, but then underneath this master service agreement, we have a statement of work, and then this statement of work is later amended. And then even later still, we have a statement of work 2, and this statement of work can also be amended and so on. So now as we look at this, we say, okay, well, what can happen next? A statement of work may spawn a purchase order, and a purchase order may eventually have an invoice. So when we think about vertical hierarchy, we're talking about having to understand this set of documents all together to understand the whole of the meaning of this relationship. And then we start to have horizontal hierarchies that require us to look at different document types and how they relate to one another. We can use 2 more really quick examples here. So if I'm in an R&D engineering space, I may have a research paper. And then later on, we may have another important research result. We'll call that R2. And that result may cite work or results in the first result. And then later on, we may have another research R3, and it may cite R2 and the original paper. As an example of a horizontal hierarchy, we may eventually work outward and get to a patent filing. So this might be a US patent. And later still, we may have productization and product documentation. So again, in this example, we have a lot of research work that gives us sort of the epistemology of the ideas and the citations of who is creating the ideas. And then in the horizontal space, we have the evolution towards US patent filings and productization. A last very short example would be people who move physical goods around the world, supply chain type people, where we have e-bills of lading. And when we ship something expensive, we probably have a certificate of insurance that shows that we've insured what we're shipping. And then we're going to eventually send this to someone who's going to have a shipping receipt of what they believe they received. And if they think they received something that was damaged, they're going to file a claim. And the claim is going to relate to who we shipped to, and it's going to relate to our certificate of insurance. So again, to understand the relationship of the shipper, we need to understand the e-bills and the COIs. And then to understand the horizontal relationships, we need to understand how e-bills relate to shipping receipts and how the certificate of insurance relates to a claim. So we've introduced documents as a data problem, and we've discussed how documents are fundamentally constructed with language and data types like numbers and dates. Okay, so let's talk about the breakthrough. The breakthrough and the big new tool that we have today are these GPT models, which are foundation models that allow us to develop these large language models. And GPT stands for Generative Pre-trained Transformer. Okay, so a lot of the technology that's in these GPT models is borrowed from neural nets. But what we have is we have the ability to apply these transformers to a language which is finite. So let's talk about the English language here. So in the English language, we have about 170,000. It's a little more than that, but we have about 170,000 words that are in the active vocabulary, right? We also know that we have, A, B, C, ... to Z, so we know we've got 26 characters. And then of course we know that we have numbers. Numbers can be represented different ways, right? Like you can have a decimal, 5.1 or whatever. But ultimately, the numbers we know to be infinite, but they're somewhat easy to recognize. So basically, you've got this mostly finite space, finite when we come to language, still infinite when we come to numbers. But ultimately, we've got an area that we can work in here. And when we consider these numbers and we look at some of the open source LLMs that are on the market, We know that this type of a space ends up being greater than 600 billion parameters. So to parameterize a space that looks like the English language, we end up with a little over between 600 and 700 billion parameters. Okay, now let's jump for a minute into, okay, we talked about generative pre-trained transformers. Let's very briefly hit on what that's all about. So basically, you know, we're trying to have inputs. We want a machine that can take inputs and give us, you know, expected outputs, right? So we're trying to create inputs and outputs that make sense. Our inputs are going to be language, right? They're going to be, we're going to call them tokens later on. But basically, we're trying to do embedding, which is taking vocabulary and turning it into math. So this is basically one-dimensional vectors, sort of looking at the concept of distance between things in a one-dimensional space. And then from here, we start using transformers. And what transformers do is they start to create a really high dimensional space, so that instead of just looking at the distance, you know, between two things, you start to see two-dimensional representations, you know, that look something more like this, if you've ever, you know, looked at any of the literature that's out there. So this is kind of like 1D, and this is like a 2D matrix, you know, representation of a multi-dimensional space. Okay. Attention and normalization start to deal with grouping. So this idea of grouping, and normalization is this fancy way to move from like one-dimensional vectors up into really big matrices, and then chunking things into like smaller groups of matrices. Okay, this is all fancy math that you can go look into more if you'd like to. And then when we get to softmax and attention output, softmax is a really fancy probabilistic algorithm that basically looks at input tokens and then does a bunch of this computation to create a set of output tokens that will have probability 1, meaning this is the thing that's sort of determining what is the most likely thing that you're expecting to see based on what you put in. The attention output, as we said, is kind of related to the most likely. In attention output, this is the layer where you say, hey, I want my answers to sound like you're from New York, or I want my answers to sound like you're from Silicon Valley. So if you're going to do stylistic type of outputs, this is the layer that you're usually operating in. And then when you project vocabulary, this is literally your output, right? So we have this new exciting tech, and we go back to our problem of having a document. Okay, so we have a document, and actually we have a lot of documents, but let's look at one document here. And this document may have 1,000 words in it. Okay, what we're trying to get to is we're trying to get to a data model representation of this document, and the data model that we care about might be small. We might really care about 20 really key data points or 50 key data points out of this larger document. The mistake that people make is that to get from here to here, we tend to want to think about a reductionist process. You know, we're taking this document and we're whittling it down, you know, to find these couple of key points that we want to end up with over here. But in reality, what happens is we have this huge expansion that's happening, right? So first, you know, we may apply an OCR. And as we apply an OCR, right, the data expands from 1,000 data points to maybe 1,000,000 or 10 million data points. Then we apply some natural language processing, and we develop still more data, so we're expanding. And then in the end, we get to something like an LLM, and then we deal with even more data still. So really what we're doing is we've got this expansion that's happening, and then that's going to allow us to get back to contracting to this data model which is where we're going to make everybody happy, right? Is if we can really get this representation of the data that we care about. Okay, so this is our data layer. This is our LLM breakthrough, and these are some of the older technologies that work together in this overall pipeline. And so what remains for us is to talk about how we can develop agentic workflows or develop agents to do this work for us. Now that we've talked about some of the newer technologies, in particular LLMs, and how LLMs can play with other technologies we're more familiar with, like OCR and NLP, now let's talk about how this comes together in developing agents and what agentic workflows are versus, say, traditional workflows. So let's start by naming a couple of agents and thinking about what would be some useful agents. So we could have an inspection agent, and an inspection agent could take a file and do some deep file inspection, right? So an inspection agent may take checksums, it may look at word spacing within files, it may look at file length, it may look at file size, it may look at aspects of what kind of contents are in the file, okay? Another agent that could be useful could be an OCR agent. So we go out and we take our most performant OCR engine that we really like, or in some cases, if you have a multimodal model, some folks are starting to look at LLMs themselves as being able to replace the OCR. But essentially, this agent can take our image data and transform it into text data, alphanumeric data, tables, etc. We could have a vectorize agent. Vectorize agent is probably almost certainly pretty heavily involved with an LLM of our choice. The vectorize agent is gonna chunk up our document into tokens and groupings and run it through an LLM to develop some of that vectorized magic that we just spoke about. The splitter agent, we can make a splitter agent. Here it is. The splitter agent could be an agent that takes a look at everything we've done up to this point and makes determinations and learns where documents should be split, right? So we may find that we want to split documents into multiple documents in cases where maybe we got sloppy and combined a lot of multiple documents into one before we processed. The extraction or an extract agent can be another agent that we create. And the extract agent, could be key in taking all that data that we described and helping us get back down to identifying that really critical data model that we talked about. So the extract agent is gonna have a lot of prompting. It's gonna have a lot of automated prompting that's gonna line up with the data model to allow us to identify those key data points. And then, lastly, with our little example we're working through here, maybe we have a match or a matching agent. And the matching agent, has access to all this metadata, and the matching agent is doing some of that magic that we were talking about, to help us establish those horizontal and vertical hierarchies so that we take our swarm of documents and we start to understand the documents, logically, holistically on a logical standpoint or more horizontally in terms of transactional standpoint. So if we kind of look at how this is arranging itself, it's tempting to think of agentic workflows in sort of a linear framework, which is similar to how we would probably set up a data pipeline prior to taking an AI approach, right? We tend to think about inputs and outputs, but an output from one stage becomes an input to the next stage and an output, and then the output becomes an input to the next stage, and so on. And so what we're really getting to today, when we think about rearranging these types of sequential workflows, which we might describe as deterministic. Okay, what we're really getting to today is, maybe we can arrange agentic workflows which are more autonomous and which are triggered by events such as new data arriving into the area where we're giving these agents scope to operate. And perhaps we can create interactions where these agents are looking at the work of the other agents and then they're doing their useful piece of the work, right? And so what the possibility that we open up here is not only autonomy, which could lead to efficiency in computing resource use, scalability, but we're also kind of entering this non-deterministic space, which potentially opens up a lot of new possibilities that we haven't yet considered.